Okay, so the goal of today's lecture is just a review for the midterm. And so as a reminder, the midterm is going to be this Wednesday at the regular class time. It will be in class, so you have, if you've been following the lectures from home or wherever, you do need to go to your classroom for the midterm itself. So that's at School of Mines. Connie will proctor it, and at USD, I will go to the normal DDN room and proctor it there. So I don't know if Michelle, for example, I don't know if you usually go to the School of Mines, but for the midterm, you'll have to be in class, and I'll run the DDN at the same time if you guys have questions during the exam. So today I just wanted to do just a series of problems, just so you get more practice seeing problems, problems that are of the difficulty that I would expect you to know how to solve on the midterm, and also so you can see sort of, at least when I go through these problems, the sort of logic or procedure in doing these. Do you guys have any questions about the midterm or more general questions? Otherwise, I had maybe 2 or 3 problems that I had planned on going through, and these are of the difficulty that's on the midterm. And I'll point out that some of the problems that were on the assignments, of course, are harder than what I would expect you to do without the internet and just in class. So the midterm will cover all the material up until assignment 2. So yeah, chapters 1, 2, and 3. So I've posted the solution for assignment 2, but obviously I haven't had time to mark them yet. So let's start with a few, I'm just going to go through a few problems, and you guys feel free to stop me and ask questions if you have any issues with solving these types of problems. So the first one I want to do is I'm having problems with my tablet now. Calculus of variations problem. Why is this not working? Okay, so let's do a problem on the calculus of variations. So let's find the curve that minimizes a surface of revolution. So what do I mean? So I apologize, and this is going to be a terrible looking diagram. So let's say I have 2 points in the XY plane. Okay? And I want to calculate the shape of the curve here between these 2 points so that when I take a 3-dimensional surface the area of that surface is minimized. So I apologize for the terrible diagram, but I hope you understand what I mean, right? So we have in the XY plane 2 points, and then I draw a surface by moving the line that connects the 2 points around the y-axis, and that creates a surface. And I want to find the shape of that line that minimizes the area of that surface. So for example, so the x1 and x2 draw circles around the y-axis, right? So you could think of, for example, as those 2 circles being wire hoops, and you have a soap bubble that connects the 2 hoops. And that soap bubble will take the shape that minimizes the total surface. All right. So the question is, what is the shape of the curve? Y is a function of x that will minimize this total surface. So what we do is we take a small piece of the surface here, and we call that dA. So dA is going to be equal to 2 pi x. All right, so dA is a very small surface. And so if you unwind it, like the top part of the rectangle is 2 pi x, the circumference. And then the vertical part is what we'll call ds. So it's the small elements of line between x1 and x2 that forms the other side of the rectangle, right? So if you unwind that small element of surface, its area is 2 pi x dx. Times ds, sorry. So what we want to minimize the total surface of the thing, S, and that's going to be the integral. Well, I guess we don't put limits on it yet. It's the integral of dA. It's the sum of all the little surfaces. And so that we can write as the integral of 2 pi x ds. Okay, so now our integration variable is s, and then the function depends on x. So we need to make this somehow dx, right? So we can integrate over x, for example. So ds is a small line element on the curve that goes from x1 to x2 in the xy plane. So we can write ds as, and this is a very common trick, as the square root of dy squared plus dx squared. And the calculus of variation, you almost always have to write the line element ds, and this is the best way to write it. And then you can do some more mathematical trickstery to write this as dy squared over dx squared plus 1 dx, or dy by dx all squared plus 1 dx, or 1 plus y prime square root dx. Oops. So what we really want is the integral s from x1 to x2 of 2 pi x square root of 1 plus y prime squared dx. We want the stationary value of this. So that looks exactly like something of the form integral of L dx, where L is x times the square root of 1 plus y prime squared. So if you really want to keep the 2 pi's, you could put them there. The 2 pi's are constant, so they're not going to matter. So now if we want to find the stationary value of this integral s, we know that we can use, it's interesting, it shows the title again. We know that we can use the Euler-Lagrange equation, which tells us that d by dx, total derivative, of di-L by di-y prime minus di-L by di-y equals 0. I'll just rewrite L here. L is equal to x times the square root of 1 plus y prime squared. So if the Euler-Lagrange equation is satisfied, then the function y of x results in the integral being stationary, which is the problem, what we want to find. Oops. So let's do this. First of all, L doesn't depend on y, right, explicitly, so that second term will be 0. So now we're left with d by dx of di-L by di-y prime. All right. So di-L by di-y prime, partial derivative, right? So we have x. So that's the same if you want to write it as x times 1 plus y prime squared to the 1/2, right? So that's x times 1/2 times y, 1 plus y prime squared to the power of minus 1/2, and then the chain rule times the derivative of what's inside, d by dy of 1 plus y prime squared is 2y prime. So that's equal to, I'll just cancel the 2's, d by dx of x y primed times 1 plus y prime squared to the minus 1/2. And that's equal to 0. Remember, our goal is to find the function y of x. And so somehow we're going to end up for a differential equation that gives us that function. So here's another trick that comes often in these calculus of variation problems. If d by dx of something is equal to 0, that means that thing is constant. So since d by dx of that thing in the middle is 0, I'm going to write this as xy primed over the square root of 1 plus y prime squared. That's just the 1 plus y primed to the power of minus 1/2, right? That's got to equal to some constant k. So let me manipulate this a little bit, because I want to get a differential equation. So I want to get dy dx equals something. So let's square everything and bring the 1 plus y squared to the other side. So we're left with x squared y prime squared equals k squared times 1 plus y prime squared. I'll just expand out that term, so that's k squared plus k squared times y prime squared. let me bring the y prime squared to the other side. So here we have y prime squared times x squared minus k squared equals k squared. So the strategy is often the same, right? Try to isolate y prime. So that gives us that y prime is k over the square root of x squared minus k squared. That's a separable differential equation. dy by dx equals k over square root of x squared minus k squared. So we're lucky. Separable differential equations are easy. So we have on the one side integral of dy, and that's equal to the other side of integral of k over square root of x squared minus k squared dx. And so at this point, we're not mathematicians, so we don't care so much how you solve this. So the way I solve this is I look it up. And when I look it up, I get that y equals k of the arc cosh, hyperbolic cosine, of x over k plus b, where b is some integration constant. So we have two integration constants, right, k and b. So those could be found by specifically plugging in the value of y and x for 2 points of surface of revolution, right? So you can plug, you know, x and y for two different points, so you can figure out what k and b are. And you could write, if you wanted, x equals k times the cosh of y minus b over k. If you wanted to write it the other way around. No, so I would never expect you to do an integral in the exam. There are some integrations or differentiations that you may perform. They're either trivial or they're given to you. So I give you, for example, one of the formulas on the formula sheet is the derivative of cosine is minus sine. So there's not going to be anything substantially more difficult than that mathematically. So yeah, so just to be clear, for the exam, you're allowed 1 page of notes, handwritten, double-sided, and then the exam may or may not provide some formulas. And I sort of hinted that it does. Okay. And so then it turns out the solution of this thing is, I think it's the same answer as the catenary problem. Okay, so any questions about the general method of how you set up the integral and then find the stationary value by applying the Euler-Lagrange equation? Okay. Let's now do a couple of Lagrange dynamics problems. So let's do the one that was in assignment 2. That was problem 2. So in assignment 2, problem 2, we had, and this is mainly so I can show you a procedure for solving almost all of these problems. Okay. So we had an XY coordinate system where I set up Y pointing down. We had the fulcrum of a pendulum. Of mass m. And that fulcrum of the pendulum was moving downwards with this constant speed, v. Yeah, so to answer Kevin's questions, you have to go to class for the midterm. Okay. So I want to show you a procedure that works pretty much for any of these Lagrangian problems. Okay. So step one is find out the number of degrees of freedom. So in this case, there's only 1 degree of freedom, theta, because the speed of v of the fulcrum is given. So you can always find, given the speed, where the fulcrum is. And so then if you know where the fulcrum is, you can specify where the pendulum is by simply specifying theta. And so that's probably the main physics step, is to figure out how many degrees of freedom there are and what's a good degree of freedom to use. So there's 1, and we'll choose theta. Step 2 is to write the coordinates in terms of the generalized coordinates that you've used. So we're choosing theta as the generalized coordinate. So we only have this one mass, so we have to write out the x and y position of the mass in terms of theta. So x of the mass is minus L sine theta. And then the y position of the mass, if the fulcrum was at the origin at time 0, the fulcrum has moved in the positive y direction by a distance v times t, right? And then the mass itself is another distance L cos theta from that. Okay. So 3 is to write out the generalized velocities. So first we want x dot. So x dot is the d by dt of L sine theta, right? So L is a constant. And so that gives us, by the chain rule, minus L cos theta, and theta depends on time. So there's a theta dot at the end. Okay? Similarly for y dot. So d by dt of y dot, the first term is linear in t, so we get a v. And then the second term is going to be minus L sine theta, theta dot. Okay? Step 4 is to write out the kinetic energy. So T can always be written as a half m using the Cartesian coordinates x dot squared plus y dot squared. So using our result, we have a half m x dot squared is L squared cos squared theta, theta dot squared. And y dot squared is v squared minus 2v L sine theta, theta dot, plus L squared sine squared theta, theta dot squared. Okay. So this kinetic energy often simplifies, especially when you're using polar coordinates. So you'll note that we have the L squared cos squared theta dot squared and L squared sine squared theta dot squared. Okay. Can people hear me? It looks like I got cut off. Start sharing. Yeah, I'm trying to get the video back. I think I just have a weak wireless here. Uh-oh. Hold on. Okay. Alright, looks like we're back. I can see my wireless signal is weak, so this could happen again. It's actually in my office at USD. Alright, so as I was saying, it hasn't quite recovered, has it? Alright, sorry about that. Okay, so as I was saying, often when you're doing this in polar coordinates, and you saw it in assignment 2, problem 1, there's some simplifications. So in this case, I can group the cos squared sine squared theta term. And so writing out the kinetic energy, I now have a half m L squared theta dot squared plus v squared, and then the cross term, minus 2vl sine theta, theta dot. Alright, step 5 is to write out the potential. So in this case, V is minus mgy. Why is it minus? It's because I made an awkward choice of having the y-axis point downwards. And so in that case, the potential energy goes opposite of the y-coordinate. And so that's equal to minus mg, and then my expression for y, which was Vt plus L cos theta. Okay. So that'll be now step 6. We can finally write out the Lagrangian, which is t minus v. So in our case, it's a half m times L squared theta dot squared plus v squared minus the cross term minus 2vl sine theta theta dot. And so it's minus v, so it's plus mgvt plus mgl cos theta. And now step 7 is to apply the Euler-Lagrange equations. So we only have the 1 degree of freedom, theta, so we only have to do it for theta. This is an awfully slow connection. So the first thing we want to know is di L by di theta dot. So if I look at L and how it depends on theta dot, there's 2 terms. There's a half ml squared theta dot squared. So if I d by d theta dot of that, I get ml squared theta dot. And the second term is a half m times minus 2vl sine theta theta dot. So the half cancels the 2, and if I take the derivative of the theta dot, it's just linear in theta dot, so I'm left with that should be a minus, not an equal, minus mvl sine theta. But the term that I really need in the Euler-Lagrange equation is d by dt of that. So d by dt of di L by di theta dot is d by dt of the line above. So in the first term, m and L squared are constants. So d by dt of theta dot is theta double dot. So I have ml squared theta double dot minus, and now again I have to apply the chain rule to the sine theta, so I have minus mvl cos theta theta dot. And then the other term that goes in the Euler-Lagrange equation is di L by di theta. So looking at the terms, there's a term in theta in the kinetic energy, right, a half m times 2vl sine theta. So the derivative of that is, so the half and the 2 cancels, so I have minus mvl cos theta theta dot. That's the derivative of the first term. And then the second term is the mgl cos theta. So the derivative of that will be minus mgl sine theta. So if I call this A and this B, the two terms that I just calculated. And the Euler-Lagrange equation tells me that A minus B equals 0. Or that ML squared theta double dot minus MVL cos theta dot plus MVL cos theta dot plus MGL sine theta equal to 0. And again, it's often true in these specific cases that that cross term cancels. And then I can also divide out of each term an M and an L. And so I'm left with L theta double dot plus G sine theta equals 0, or theta double dot equals minus G over L sine theta. And so, does this result make sense? Yes, it does. So this is the equation for a simple pendulum. Now in our situation, we had a simple pendulum that was moving at a constant speed v. But that pendulum moving at a constant speed v just keeps it in an inertial frame of reference. So we could have set up a new coordinate system, an inertial coordinate system that's moving with a speed v, and then it looks exactly like a pendulum, because it is a pendulum. Okay, so the result should not surprise you, and it turns out the v's canceled everywhere. Any questions about that? All right, so let's do another pendulum. So let's draw an X and Y coordinate system. Let's draw it upright this time. And let's draw a circle centered at the origin. And the fulcrum of our pendulum is going to move around that circle. So the fulcrum moves around the circle at a known fixed angular speed, omega. And so we'll find the equation of motion for the pendulum. So again, step one, how many degrees of freedom? Well, again, the fulcrum of the pendulum, its motion is completely specified. So given the location of that fulcrum, we can find where the pendulum is simply by specifying the angle theta. So there's 1 degree of freedom. And again, we'll choose theta. Step 2 is to write out the coordinates of the mass for which we're going to do the equation of motion. So let me first call the fulcrum point P. And so the position of the fulcrum is a function of time. So let's call that x sub p. I guess we need to know the radius of the circle. So let's call the radius, let's say the circle has a radius r, capital R. So the point, the fulcrum, its position its x position as a function of time is going to be r cos omega t, and then its y position is going to be r sine omega t. So the pendulum's now coordinates x and y. So x of the pendulum is going to be equal to xp plus L sine theta, and the y position of the pendulum is going to be yp minus L cos theta. Right? So if I plug in xp and yp, that's r cos omega t plus L sine theta for the x position, and the y position will be r sine omega t minus L cos theta. So now we've written out the position of the mass of interest in terms of the generalized coordinates. So our next step is to write out the generalized velocities, or the velocities, the time derivatives of those coordinates. So x dot is d by dt of r cos omega t plus L sine theta. So d by dt of r cos omega t is minus omega r sine omega t. And d by dt of L sine theta, that's our usual L cos theta, theta dot. Similarly, y dot, the derivative of the first term is omega r cos omega t, and then plus L sine theta, theta dot. Step 4, we now want to calculate the kinetic energy. So let me just hold off the half m term for a second. Just do x dot squared plus y dot squared, since we're clearly going to have a few terms here. So x dot squared is going to be omega squared r squared sine squared omega t minus 2 times the cross term, so minus 2 omega r sine omega t L cos theta, theta dot, plus L squared cos squared theta dot squared, plus the y dot squared term, which will be plus omega squared r squared cos squared omega t, plus 2 times the cross term, 2 omega r cos omega t L sine theta, theta dot, plus L squared sine squared theta dot squared. I guess I forgot to write in the thetas after the sine squared and the cos squared. You're asking why xp is r sine omega t. Well, for once, I'm actually using this is the circle, right? So the fulcrum's moving in a circle, and I've defined the angle omega t to be sort of the standard angle that you would take from the x-axis. So then the x component of that is cos omega t. So I mean, I should have been more clear about that. It's like our physicist's habit of taking the pendulum angle as the polar angle from the vertical rather than from the horizontal. So now, because we've done so many pendulums, you're used to x going with sine of the angle rather than cos. Did I answer your question, Lou? Yeah, you'll absolutely get the same answer. And so in the final answer that you do, if you want to switch it, and that's actually a good exercise, go ahead and do it the other way. The final answer, you'll have a cos instead of a sine when you see what the final answer is. But it will be exactly the same. Because basically you use the property that, cos of pi over 2 minus the angle is sine of the angle. You're just redefining it. Okay. So this simplifies a little bit, our x dot squared plus y dot squared. So as you've noticed, we have the first term in x dot squared is a sine squared omega t, and the first term in y dot squared is a cos squared omega t. So those sum up. So the first term on each line gives omega squared r squared. Now the cross term you can't do much about. So let's first look at the last term. And so the last term comes up in every single pendulum. L squared cos squared theta dot squared, L squared sine squared theta dot squared, cos squared plus sine squared equals 1. So we have plus L squared theta dot squared. And then we have the cross term. So the cross term, I'm going to factor out a plus 2 omega r L theta dot, right? And then I'm going to write this as cos omega t sine theta minus sine omega t cos theta. I swapped the order of the terms so that it looks pretty. And it looks pretty because of the double, I guess it's not called a double angle formula. It's the subtraction and addition of sines. So recall that sine of a minus b is equal to sine of a cos of b minus sine of b cos of a. That's exactly what we have in here, right? So that means I can rewrite this as omega squared r squared plus L squared theta dot squared plus 2 omega r L theta dot. And now I have sine of theta minus omega t. So the kinetic energy is a half m times this term. Right. So our next step, which is step 5, is to write out a potential energy. So I have my y-axis pointing upwards, right? So it's just going to be mgy. mg. And so if I look up what I had for my y-coordinates, which was yp minus L cos theta, so that's mg times r sine omega t minus L cos theta. Okay, so step 6. Let's write out the full Lagrangian, t minus v. So that's equal to a half m omega squared r squared plus a half m L squared theta dot squared plus a half m times 2m, so the half and the 2 cancels. So we have an m omega r L theta dot sine okay. So I got cut off, but I think I'm back now. And I think, yeah, you can hear me. Okay. So we have, I was writing out the cross term, and then the cross term was, there was a half m times 2 omega rl theta dot sine of theta minus omega t. The 2's cancel, and I'm left with m omega rl theta dot theta minus omega t. That's t. And then minus v, so that's minus mg r sine of omega t, and then plus mgl cos theta. Okay. All right. Step 7 is to now do the Euler-Lagrange equation. So the first term that we want is di-L by di-theta dot. So first term doesn't have a theta dot. The second term, only theta dot. What's ml squared theta dot squared? So the derivative with respect to that is ml squared theta dot. And then, excuse me, the next term also has a theta dot. So the derivative with respect to theta dot of that next term is m omega r L sine theta minus omega t. What we really want in the Euler-Lagrange equation is d by dt of this thing. So we want d by dt of di-L by di-theta dot. So the first term, the only thing that can depend on t is theta dot. So that gives us ml squared theta double dot. And then the second term, we're going to have to do the chain rule because the sine of theta minus omega t depends on t, right? Both theta and omega t depend on t, right? So that's going to be m omega r L, and then d by dt of sine of omega minus t is going to be cos of theta minus omega t times the derivative of theta minus omega t, which is theta dot minus omega. Okay? And then we also need di-L by di-theta. So di L by di theta, the first term that depends on theta is the m omega r L theta dot sine theta minus omega t. So the derivative of that with respect to theta is m omega r L theta dot cos of theta minus omega t, and the derivative with respect to theta of theta minus omega t is just 1, right? And then the next term that depends on theta is the last term in the Lagrangian, the mgl cos theta. So if I take the derivative of that, I get minus mgl sine theta. So if I call the term above A and the term we just calculated B, then the Euler-Lagrange equation tells us that A minus B equals 0. So let's write that out. So when I write the A term, I'm going to write it in 3 terms. So I'll make a theta dot term and a minus omega term. So I have ml squared theta double dot plus m omega r L cos of theta minus omega t times theta dot. And then the second term is going to be minus m, so it's the whole thing times omega, or minus omega, so there's an omega squared, minus m omega squared r L cos theta minus omega t. And then minus the term that I called b. So minus m omega r L theta dot cos theta minus omega t plus mgl sine theta. And that whole thing equals 0. So again, we have this fortuitous cancellation of the theta dot term. And then each term has an m and an l that I can eliminate. So I'm left with L theta double dot minus omega squared r times cos of omega t minus theta minus omega t, sorry. Plus mgl sine theta equals 0. If we want, of course, we can isolate theta double dot. So theta double dot is 1 over L times omega squared r.
Yeah.
When you say
Your
that
last
louder.
term, MGL sine theta, there's only one L. You already dropped the L.
You're right. Thanks for pointing that out. And the M also needs to disappear. So you get theta double dot equals 1 over L times omega squared r g sine theta. So does this make sense? Oops, sorry, I forgot the cos theta minus omega t in there. Oops. It's omega squared r cos of theta minus omega t minus g sine theta. Well, if omega is equal to 0, then you recover the normal equation of motion for a pendulum. So it doesn't make no sense, at least. Okay. And this is generally important when you're working through these things to make sure everything matches, that the units match, and things like that, right? So when you have two terms that are added, they must have the same dimension. So the omega squared r has the same dimension as g, because omega has dimensions of 1 over time squared, r has dimensions of length, and g has dimensions of length over time squared. Okay. Similarly, when you're doing the expansion to get the kinetic energy, that usually has a lot of cross terms in it, and they should always be, all terms are dimensions of velocity squared, right? So there's always a theta dot with an omega or a theta dot squared, and then a length squared usually. Okay, so these are little checks to make sure along the way that you're not making mistakes, just to check that the dimensions of the terms you're adding together are the same. Right? You can't add apple and oranges. So last, I was just going to make a comment on an example problem, but I wasn't going to work it out fully. Again, the pendulum. So let's have a normal x and y axis with, y pointing up. And this is one you can work on at home. Make sure you understand how to do it. It's easy to find the solution online. But I'll set it up for you. So that's the pendulum where it's attached on a spring. So it's fixed at the origin, but there's a spring instead of a string. It's a massless spring. So you would ask yourselves, how many degrees of freedom does this have? And so this has 2 degrees of freedom, right? It has theta, obviously, but it also has how far is the string stretched, is the spring stretched. All right, so there's a degree of freedom that's the distance along the spring. Now you can choose whatever degree coordinates, generalized coordinates you want for those 2 degrees of freedom, right? You can choose x and y as those coordinates, but they might not be the easiest. And so a good choice is, for example, theta, and let's call d. So let's say that the length, the distance from the mass to the origin is the distance L plus d, where L is the unstretched spring, and then d is the distance that it's stretched or compressed by. So you could choose, there's 2 degrees of freedom. And you can choose, for example, theta and d. So the d coordinate is kind of like, you have polar coordinates, right? Because you have to specify the distance to the origin and the angle theta. So you could write the x position of the mass as L plus d sine theta, I guess. And then the y position of the mass would be minus L plus d cos theta. Now, 3, when you want to calculate x dot and y dot, you have to be a little bit careful, right? Because d depends on time. look awkward. D by dt is not equal to 0, since d is a function of t. So you can work out the kinetic energy, and already knowing the results from polar coordinates, because you worked that out diligently in assignment 2, you can find that the kinetic energy T is a half m times d dot squared plus L plus d squared theta dot squared. That sort of makes sense, right? It's like there's a component that's along D, and then there's a component that's tangential. And then the rest of this is actually fairly straightforward, right? V is again mgy minus mg L plus d cos theta. And then you can write out the Lagrangian and take the derivatives. And so when you do this, at step 7, you're going to end up with an equation with theta double dots and an equation for d double dots. And these could be coupled, right? There could be a d double dot in there, and there could be a theta double dot in there. In principle, they could be coupled. But I hope that I showed you a procedure that's fairly straightforward to follow to solve all these problems. And if you can do the problems that we just did in this review, you won't have any problem on the midterm. Yes, Kevin? I can't hear you at all. Do you want to type the question? Ah, yes, sorry. I completely forgot. Of course. You're absolutely correct. Yeah. V has a half kd squared. Yes. Absolutely. That's what I get for not working it out myself. Okay, so that's all I was going to do today. Is it okay to leave? Yeah, in general, and this is again also for the assignment, I'm mostly interested in, can you get the equations of motion and down to a solvable problem that if you give it to a computer, the computer can understand it. In an exam, I will usually give you things that you can work out to the end, or I'll tell you, show that it can be written in this way. And then for the assignments, as grad students, I expect you to go look up how to solve it. But I don't usually dock you that many marks if you get the equations of motion and don't solve them. So one good example was this last assignment where question 3, when you were doing the sphere rolling on another sphere, I wouldn't expect you to be able to solve, even though you don't need a computer to solve it, it did require a pretty clever trick to get rid of one of the derivatives. You had to do like a little integral and realize that you could rewrite something in a different way. I wouldn't expect you to, think of those clever tricks in a sort of exam situation. When you're doing assignments, I certainly expect you to go look it up and how to do it. But for assignments, then no. No, I don't have any Lou, and you're right, in the first lectures we covered how to solve differential equations and the Runge-Kutta method. Those were just tools that I was giving you how to solve the equations when you're doing assignments. But in an exam, it wouldn't be appropriate for me to ask you that kind of question. So I'm really just interested in, do you understand the physics? Like, do you get the equations of motion, and do they make sense? If I see that you've done an equation of motion or a kinetic energy where the terms don't have the same dimensions, you're going to lose a lot of marks, because that's stuff that you should realize. But in the end, you know, even if you screw up the sign of a derivative, then this is not the end of the world. This is not as important. Okay. Any other questions? I hope you'll find the midterm straightforward. Okay. It's two relatively short problems. Like I said, make sure you can do the problems that we just did here. I mean, if you don't have any questions of what we just did in class today, then you're not going to have any problems on the midterm. And I'm actually USD this week, which of course doesn't help the people at School of Mines. But you're always free to email me, and we can do a Google Hangout or a Collaborate session, and I can help you work through a problem. Just because I'm not there physically, I can still be there virtually. Okay. So if there's no more questions, then I guess that's it, and I'll see you guys all in class on Wednesday. Okay. Bye.